All right, guys, so we're going to take a look at what's called organic nomenclature, which is just a fancy chemistry way of saying we're going to learn a new naming system of naming organic compounds. And so the thing that we need to understand first about organic naming is that organic compounds are always named by using a parent chain. And we'll look at hydrocarbons in just a minute. But essentially what we have is we have carbons that can be attached to each other, and they can be of a certain length of carbons. So we could have a chain of carbons that just has one carbon in it. So not really a chain, but it's still one carbon long. And so we give that a name, and in this case it's called meth. That's the prefix that we use. If it's 2 carbons long, then we give it the name eth. 3 is prop. And you can see the rest here, 4 bute, 5 pent, 6 hex, and so on. And a lot of these are similar, and some that you are already familiar with, many that you're already familiar with. And what I'm going to do is in the next series of clips as we go through, show you how these parent chain names are used in naming particular types of compounds. These clips hopefully will be fairly short, so stick with me. If you need to pause and go back and write some things down, then go ahead and do that. And then at the end of all of it, I should be able to give you a list of naming rules that you can kind of follow and hopefully keep you on the right track as you do this. So stick with me here. We're going to get started with our first group and how to name them. Okay, so we're going to look at groups of hydrocarbons first, and the thing I want to point out is that hydrocarbons are the simplest organics. Hydrocarbons are made of carbons and hydrogens, and that's it. Well, they may be made of other things as well, but we'll kind of look at that as we kind of look into derivatives of hydrocarbons and stuff like that. But the basic, most simplest group that we're going to look at to start with is the group called the alkanes. Now, alkanes have a little bit of a description to them that separates them from the rest, and so you should write this down as part of your notes. Everything that's on here on the board you should jot down. First thing that we need to point out is that alkanes are saturated molecules. Now by that what we mean is that alkanes are compounds that have carbon-carbon single bonds only. Okay, you'll see as we carry on throughout the unit that there are some compounds that have carbon-carbon double bonds and some compounds that have carbon-carbon triple bonds. And maybe have double bonds elsewhere in the molecule as well. The definition for alkanes in terms of being saturated is that every carbon is attached to another carbon with a single bond. That's what that means. Aliphatic simply means that it doesn't contain the molecule benzene. Now, what is benzene? We'll get to in a later clip, a later video as the unit rolls on. But for right now, just jot that down in your notes. Alkanes are aliphatic. And they have this generic formula that they all follow. So I've got 3 examples up here on the board of 3 different alkanes. You can see that this one has 2 carbons in it. It's 2 carbons long. And so if N is 2, then I would put 2 in for this as well. And I do the math, and you can see that my chemical formula turns out to be C2H6. So it's a bit of a quickened way that you can calculate the chemical formula for a compound. Now for this, it would be probably just as quick to count how many carbons and count how many hydrogens. But if we have an alkane that's got 15 or 20 carbons in the chemical formula, then it's a lot quicker to use this formula when we identify it as an alkane. This formula is for alkanes. You can see that this formula matches for all of these. So C4H10. C5H12. And if we go back to the previous clip of what the names of these would be, because these are alkanes, then I have to name the parent chain. The parent chain is how many carbons is this long. This one is 2 long, this is 4 long, this is 5 long. So this guy right here would be ethane. And this one right here would be butane. And this one right here would be pentane. You've heard of some other compounds that I've had you learn as we've gone through Chem 20 and Chem 30. Something like propane. Prop means 3 carbons long, and so we have C3H8 for propane. Another common chemical that you might be familiar with is octane. Octane is the gas that we stick into our vehicles that makes them run in the combustion engines. And oct means 8, so that's 8 carbons long with hydrogens all the way around. And that's just really the basic way of how we name alkanes. All of these ones here you need to know from numbers 1 to 10. And if it's just a simple alkane, then it would just be F-ane. That tells me 2 carbons long with hydrogens all the way around. It's an alkane, so I know it's saturated. All the carbon-carbon bonds will be single bonds. And that's it. So we're going to jump into a few more things here, so hang with me. All right, something else that you need to know as we kind of spread ourselves through this unit and look at the different types of diagrams that we have to draw. There's actually 3 that you have to be able to read and interpret and draw yourselves. And so here are here are 3 examples of, or 1 example of each kind of those diagrams. So here we've got our regular sort of most expanded type of diagram called a structural diagram. We did a lot of these in Chem 20 with the lines, everything showing where everything gets bonded. The trouble with these sometimes is things can get pretty crowded in where things are at. And so what we oftentimes try to do is we try to implore some diagrams that are a little bit more condensed in their versions and their structures. And so you can see we've got a condensed structural diagram of the exact same molecule written right here. And the way that you can kind of connect these and see how they're related is you can see that you have a CH3 right here. And then you've got a bunch of CH2s. All here connected, and then another CH3 on the end. And so this is just corresponding to each one of these little segments in that molecule. Now this last one is just a line diagram, and the line diagrams just remove everything except for the carbons. The way that they're set up is that every end of the line represents a carbon in that molecule. So the diagram that you would see would be written like this, but if I were to kind of identify a few things for you in this diagram, we would have a carbon here at that end of the line, a carbon here, 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 and here. And so you can see that each one of these 3 molecules is 6 carbons long. They all contain the same number of hydrogens. We just don't stick the hydrogens in these line diagrams just for the sake of, we know they're there, we know it's a simple alkane, and so we can just simply assume that the hydrogens are there and move forward with what we're doing with naming. And so if we've got a carbon here, this carbon has 1 bond there, which means I know that there are 3 other hydrogens that have to be coming off of it to fill the octet of that carbon. This carbon has 2 bonds coming off of it, which means it can only hold 2 hydrogens. Same with these guys here, and this last one over here can contain 3 hydrogens. Again, the line diagrams don't look like this, they look like how I had it drawn originally, but you need to know that those things are there when you see those diagrams and when you draw them. So that's a quick lesson on the types of diagrams you need to know. There you go, be right back. Okay, next up is alkyl branches. We're gonna take a look at some regular alkane molecules. So we've got butane, pentane, and hexane, these guys, this is their regular organic name for those compounds. But sometimes what we can get is we can get alkane molecules that are still saturated. They still have just carbon-carbon single bonds, but they have these branches in them. So we don't have like one continuous long chain of carbons. We've got a chain of carbons, and then another couple of carbons kind of sticking off the middle of that chain. And so you take a look at this one, for example. This guy right here has a branch, what we call an alkyl branch, in the middle of this longer chain right here. So what we do when we name these organic compounds is we number the parent chain first. That's sort of the number 1 rule that you need to follow as you're naming these. So we can number parent chains from left to right, or we can number them from right to left. And so you can see I've numbered them in this case, and the numbers really in these molecules here don't really matter. But if you take a look in these molecules here, I've numbered this one 1, 2, 3 so that I can identify what is the longest parent chain that that molecule has to offer. And in this case it's 3 long, 1, 2, 3, and I have what's called a methyl alkyl branch sticking off in the middle of that parent chain. And so I just named this compound methyl propane. So I name the alkyl branch first here, and then I name what the parent chain name would be. In this case, it's propane because it's 3 carbons long. Yes, there's 4 carbons altogether, but there's only 3 in the parent chain. So the parent chain is prop, and we go propane because it's an alkane. And so this is the name of that molecule, methyl propane. You can see for this next one right here, again, we're 5 carbons long. This one has 5 carbons in this molecule, but it's not 5 carbons long, it's only 4 long. So I've numbered them 1, 2, 3, 4, and I have therefore methyl butane. So this molecule too could be flipped in 3 dimensions. Like if I've got a molecule, just because it's flipped around like this or like this or like this or like this, just because its orientation is changing in 3 dimensions doesn't all of a sudden make it a brand new molecule. So this methyl butane is actually the same as if I were to, on the paper, think of it being flipped 180 degrees like that, and I could draw it like this. That too is methyl butane. Notice that I haven't drawn all the hydrogens in. The little empty ticks here just indicate that there are hydrogens on those carbons. It just means that I haven't put them in just because it helps with being able to see the larger molecule but not having all those hydrogens crammed in to visualize what's going on. Both of these molecules are the same. Okay, so I would name this as well methyl butane, and it's just simply because all this molecule is that molecule rotated 180 degrees in 3 dimensions. So you do have to be able to identify that and notice that with certain types of molecules. Here we've got this one where things start to get a little bit more complicated. A few more rules kind of added in. This one is 6 carbon long, so we have hexane as our parent chain, and that's the name of that molecule. There's no branches, so I don't need to put any branch names here at the beginning. This one here, though, you can see is 5 long with an alkyl branch, again, sticking out of the middle. I've got this methyl alkyl branch off of carbon 2, and you can see over here, this one as well has a methyl branch off of carbon 2. I could just number this molecule like that. And that tells me that, hey, this molecule is the same as this one. It's just this molecule's been flipped 180 degrees like that, and then it's been flipped like this as well, where this alkyl branch now is on the bottom rather than the top. And it just, again, it doesn't really matter. As long as the alkyl branch is in the same place and it's got the same length of parent chain, then it's the same molecule. So the thing we need to point out, though, about this particular molecule is that we can have a methyl branch in a different location. And so, yes, these 2 molecules here are the same. So I can just get rid of this one. It's not super necessary to have that one there. This molecule has a methyl branch on carbon 2, and this molecule has a methyl branch on carbon 3. And so to distinguish between the 2 molecules, because they are different molecules, I can't rearrange this one to all of a sudden get the methyl branch on a new carbon. We have to give them a different name. And so we have to distinguish which carbon that methyl branch is sitting on. So this methyl branch is sitting on carbon 2, so we say that this is called 2-methyl-hexane. Or sorry, 2-methyl, this is not right, this should be 2-methyl-pentane. And this one right here should be 3-methyl-pentane. And so because those have different names, then those are obviously different molecules. Now, the last thing that I need to cover with you as it relates to these compounds is that you can see that butane has the same chemical formula, C4H10, as methylpropane. It also, if you were to count the carbons and the hydrogens or just do the math from that generic little formula I showed you in the last clip, it would also have the same chemical formula, C4H10. If you take a look at pentane and methylbutane, they have the same chemical formula of C5H12. And if you take a look at hexane, compare it to 2-methylpentane and 3-methylpentane, all three of those chemical formulas are all C6H14. So what does this mean? Well, anytime we have a compound that has the same chemical formula, but a different organic name, so you can see hexane is not the same as 2-methylpentane, which is not the same as 3-methylpentane. All three of those have different names. All three of these compounds are considered isomers of one another. And that's a term that you need to know right here. So again, just really quick, isomers are defined as compounds that have the same chemical formula, but a different organic name associated with them. We looked at one type of alkyl branch, which was a methyl alkyl branch. A methyl alkyl branch is just one carbon long. You can see we've got one carbon sticking off of a parent chain, a longer chain. And all this, so when it is just one long, we say that that's a methyl branch. This R just means some chain of carbons that it's attached to, and the methyl branch is going to be a CH3 if I include all the hydrogens in there. You can see I've left off all the hydrogens. Just assume that the hydrogens are present in all of these molecules. Over here, if I have an alkyl branch that's 2 carbons long, this is called an ethyl branch, or just ethyl. And so again, some ethyl branch, CH2CH3, attached to some long chain of carbons, which is just denoted by the letter R. If I'm 3 carbons long, I call that propyl. Again, CH2CH2CH3, attached to some parent chain R. And the last one is 4 long, butyl, attached to some parent chain R with 4 carbons long. And so that's what you need to know about all of that different alkyl branches that you'll come in contact with. I would say methyl, ethyl, and propyl are probably 98% of that different alkyl branches that you'll be dealing with in this class. Very rarely will you see butyl. I don't see it very often. And so it's not one that you need to worry about a ton, but it's there so that you know it. And these correspond very closely with the prefix names that we use for naming parent chains as well, right? Meth means 1, eth means 2, prop means 3, and but means 4. So there's a relationship there that you can connect with some things that maybe you've already learned. So one question you may have had from the previous clip was there were some of the names that I wrote on the whiteboard that didn't have a number in front. And you maybe ask yourself, well, why don't those ones get numbers and these other ones do? The answer to that is I only write numbers in when I have to. And so if you take a look at this example right here, you can see I can number this parent chain 1, 2, 3, or I can number it 1, 2, 3 backwards. In either case, this methyl branch gets a number 2. So in this instance, with really short parent chains of organic molecules, the number system isn't needed. I can just name this methylpropane. I don't need numbers because I can't stick the carbon on the end over here on this carbon or this carbon, because now my parent chain would be 4 long, not just 3. It would be part of the parent chain. It wouldn't be a branch anymore. Even if I were to write it like this and have the carbon there like that, now this is a continuous chain of 4 carbons. And so it's no longer a methyl branch. So there's only one place in this molecule where the methyl branch can go. Therefore, I don't need any numbers for that. So for the few examples on the board in the previous clip that didn't have numbers, that was the reason why. These were the last 2 examples that were in the previous clip, and these had numbers. And the reason why was because they're on different carbon numbers. If I number these parent chains, you can see that those methyl branches end up on different carbons. They can't, there's no way you can do the numbering where they end up on the same carbon. And so the rule that we have to follow as it relates to numbering parent chains is we have to number the chain so that the alkyl branches, all of the different branches that come off of that chain, have the lowest number possible. So in this case, I have to number this parent chain from right to left so that this alkyl branch here can be on carbon number 2. If I were to number it left to right, then this alkyl branch would be sitting on carbon number 4. So this numbering system takes priority because it gives the alkyl branch a lower number. You can see over here, I can number it left to right or right to left. Either way, I'm going to get an alkyl branch that's going to be on carbon number 3. But in this case, I still have to put number 3 on there because the alkyl branch could be on carbon number 3 or carbon number 2. And so to distinguish between those two isomers, I have to make sure that I stick a number in there. So this is going to be 2-methyl pentane, and this one would be 3-methyl pentane. Okay, moving on to the next example over here, you can see that this one has a parent chain of 6 carbons long. And that's the number one thing I have to make sure that I do before I do anything else when I'm naming organic molecules. I have to identify how long is the parent chain. What is the longest continuous chain of carbons that exist in this molecule? And for this one, it's 6. So now the next question I need to ask myself is, do I number it left to right or right to left? And you can see here I've got 2 alkyl branches in this molecule. And so if I number it from left to right, you can see that I would end up with a number 3 on this alkyl branch and a number 5 on this alkyl branch. But if I number it from right to left, I end up with a 2 and a 4. So the rule is that when you're selecting what numbering system to use, either left to right or right to left, you need to select the numbering system that yields the alkyl branches to have the lowest set of numbers. So in this case, I have 2 options. I have a 3 and a 5, or I have a 2 and a 4. And so in this case, I would select the numbering system that gives me this one because obviously the 2 and the 4 is a lower set of numbers. And so this is why I'm numbering this one from right to left for that molecule. You could have other instances. For example, you could have a 1 and a 5, say. Not for this molecule, but say for some other molecule. And another numbering system you could end up with is maybe a 3 and a 4, a set of numbers. So if I'm selecting the lowest set of numbers, this one's a little more tricky, but you just want to take the sum of the 2. So this one equals 6, this equals 7, so I would select that set for that hypothetical example. So for this molecule's name is going to have branches on carbon 2 and carbon 4. I identify both of these branches as methyl branches, and they're both methyls because they only are 1 carbon long. So that's 1 carbon and that's 1 carbon. And so the way that I name this is I go like this. So I put, because both of them are methyls, I can condense the name of this a little bit. Instead of going 2-methyl, 4-methyl, I just go 2,4-dimethyl. Di meaning 2, and then the parent chain name at the end. 6 carbons long means hexane. These are all single bonds, so it's an alkane. That's why I say hexane. So 2,4-dimethyl hexane. For this example here, we've got two alkyl branches as well, but in this case, we have 2 alkyl branches that are of different types. So how do I deal with those? What I do with these, again, is I identify first, what is the parent chain? How long is it? What's the longest chain of carbons that this molecule has to offer? And again, in this example, it's 6 long, and you can see I've numbered it. Now I've numbered it again from right to left because the alkyl branches are in the same place as the previous example. But now I've got a methyl branch on carbon 2 and an ethyl branch on carbon 4. And so the thing that you have to be careful with here is that if you have 2 different alkyl branches, you have to alphabetize them in the name. So the ethyl branch is going to come first, and then the methyl branch is going to come after that in this case. And so it'll look like this. A huge tendency that a lot of kids have as they go to name something like this is they just want to put the numbers that are lower at the front and the numbers that are higher after. And so they would go 2-methyl, 4-ethyl, and we don't do that in this case. You have to make sure that because E comes before M, that molecule has ethyl first, so we have 4-ethyl and then 2-methyl, and then the parent chain hexane at the end. Okay. So what I want you to do with this one is try it. So just pause the video really quick, give this one a whirl, write down what you think the name would be, given the rules that I've given you so far, and then hit play when you're ready to go. Okay guys, so taking a look at this molecule, the way that we're going to number this, again, is we want to identify what's the longest parent chain or the longest chain of carbons in this molecule. And something that you have to be careful with here is that you don't always just get into a groove of numbering what's the longest straight chain of carbons. Chains can be zigzaggy. And so in this case right here, you can see that the longest chain of carbons, many of you may have gone 1, 2, 3, 4, 5, 6, 7, and said 7 was the parent chain, but in fact 8 is the parent chain, because we would number it like this. And you can see that that is one continuous chain of carbons connected to each other, and so that is my parent chain. Now that this molecule is a little bit messy, sometimes what I like to do is I like to just circle what my alkyl branches are. So that I can make sure that I've identified all of them and that they're all present in my mind so that I'm not forgetting about any of them as I go to write the name. It also helps me to quickly identify what carbon each one of those is connected to. The other thing I want to just double check is I want to double check that the other numbering direction is not the numbering direction that I want. So if I were to number this like this, 1, 2, 3, 4, 5, 6, 7, 8, then I can take a look at my two sets of numbers. So for this one, I've got 3, 4, and 6. That's one set of numbers. And this one, I've got 3, 5, and 6. So you can see that the first set of numbering is the one that I want. That's the lower set of numbers, and so that's the one I'm going to go with. So I can get rid of these other numbers here that are in the way, so they're not confusing. Now I want to number this, or now I want to write the name of this. So you can see I've got 3 methyl branches. So instead of, again, going 3-methyl, 4-methyl, 6-methyl, I'm just going to go 3, 4, 6 dash trimethyl. And then I write the name of the parent chain at the very end. The parent chain is 8 long, so this is octane. And so that's what we're doing with this one, guys. One adjustment that I want to make to this example, again, you can pause the video and try it on your own now that you've got a bit of that information there for you, is let's take this carbon and let's make it an ethyl branch instead of a methyl branch. Now pause the video again, go ahead and name that one, and then hit play when you're ready to see the answer. Okay guys, so for this one, the numbering system is going to be the same. Hopefully you kept it because we didn't move any branches anywhere. So again, we've got a 3, 4, and a 6 for our branches. But instead, now we get rid of that name because this molecule is different now. Again, remember that the ethyl branch has to be in front because it has more it's alphabetically first in the alphabet. So we have one ethyl branch and two methyl branches. And so when we go ahead and write this, we end up with 6-ethyl, 3,4 dimethyl octane. So you can see some of these get really long, and that's okay. That's part of the fun of it, I think, is just trying to kind of keep track of everything and make sure that they're all good. A couple things that I want to point out as it relates to when we get to things that are really long like this. Anytime that we have numbers separating other numbers, we use commas. Anytime we have numbers separated from letters, we use dashes. So you can see that that's consistent all the way across. Also, you need to make sure that this is just one continuous line of one name. This is one name, so there's no spaces here. For example, sometimes I see kids where they write all of that stuff out and then they write octane over here by itself as a separate name. It's all one name, so don't separate the parent chain name from the rest of what you're writing down here. This is all together. And those guys are essentially the basic rules that you need to have for organic molecules. As there's a few other examples that we look at and other types of organic molecules, there's a little bit of an adjustment to some of the rules, but these are the base rules. And now as we learn other types of compounds and families of organic molecules, the naming system only changes a little bit for each one, and there's just slight modifications. One other thing I want to point out about this molecule is that you'll notice that I put the methyl here after the ethyl, even though it says di in front. So the prefixes, we don't use those when we're determining the alphabetical order of these alkyl branches. Ethyl comes before methyl, even though it's di or tri or any other prefix that might adjust what you think the alphabetization is. We just ignore those prefixes here and just take the first letter of each alkyl branch and alphabetize it that way. And then one last example over here is you can see this one that's got 7 carbons long. This is a 7-carbon chain molecule, parent chain molecule. You can see that this alkyl branch is sitting on carbon 3 and this one is sitting on carbon 5. That's if I were to number it this way. If I were to number it from right to left, they would also have 3 and 5. So no matter which way I number this, the set of numbers that I'm going to have is going to be 3 and 5. But if I have 2 different branches here, so in this case you can see I've got ethyl and methyl, then I want to select the set of the numbering system that gives the ethyl branch the lower number. Now this is really important to note. This is only for molecules where the set of numbers that I get is the same. So I number it this way. You can see that my number set is 3 and 5. And if I number it the other way, my number set is also going to be 3 and 5. So you do have to be careful with this one, because if the number sets are the same, but the branches are different, then the one that comes alphabetically first, you need to make sure that you're selecting the numbering system that gives that one the lower number. That's only if the numbering system ends up being the same for both branches, no matter which way you number the parent chain. So in this case, I could name it 5-ethyl, 3-methyl, but I'm not going to, because I can give the ethyl the 3 and the methyl the 5. And so if I can do that, I will do that. And so the name of this molecule will be (3-ethyl 5-methyl heptane). So, okay, that's it. We're moving on to the next clip. Thanks.